Hi, everyone. So last time we reviewed CPM critical path method with numerical example problems. And today we are going to talk about how the linear programming model could be constructed to determine the critical path. So let me first share my screen. Okay. Okay, so let's consider an example. So a list of activities and their predecessors, the duration of each activity is given in this table. And we'd like to find the critical path for this small project. So let's first construct the AOA network, the activity on ARC network. So I want you to recall that in the AOA network, a directed arc represents each activity or task, right? And the nodes are used to represent the completion of a set of activities. Also, let's keep in mind that while constructing the AOA network, an activity should not be represented by more than one arc in the network. And any two nodes in the network cannot be connected by more than one arc. Okay, so in general, usually the node number 0 represents the start of the network. So let's have node 0 here. That's going to be the event number 0. And an arc should lead from this node, the event number 0, to each activity that has no predecessors, because in our case, two activities has no predecessors. So we have two arcs coming from event number 0. So let's name it A, and then another one for B. Okay, like that. And the next, the both activities, tasks C and D has two predecessors, A and B. Okay, so if I have another event here, and then if I have activity C, and let's say D is like this, then of course we can make a connection to here. So let me put this, okay. So in this case, you know, activity C has two predecessors, right? They are A and B. And also D has two predecessors, A and B, right? But the problem is, if you look at these two nodes, these nodes and these nodes, these two nodes excuse me. Sorry. So if you look at these two nodes has been connected by two different arcs, right? That's the violation of one of the rules for constructing the AOA network. So in this case, what you need is to utilize dummy activity that has no time duration for that. So instead of having this activity B all the way to this node from this, we're gonna add dummy activity. So dummy activity can be represented by dash arc like this, right? So I'm gonna name it dummy activity 1, D1, like that. So in a way, both activities, C and D, has two predecessors. They are A and B, without violation of any rules for constructing AOA network, right? And the next activity E has the predecessor, which is D. So I'm gonna have activity E goes to this, okay? And F has two predecessors, C and E. So if I have another node here, and let's say you have F, then it can satisfy all of the precedence relationship, right? And we're gonna have this event, make sure all of the activities will be completed, okay? Okay, and we need to level each node here. So ignoring node number 0, you need to see which of these nodes has no predecessor. Then obviously this one has no predecessor, right? So we're gonna level 1 down here. Likewise, ignoring both events 0 and 1, we need to identify which of these nodes, which of these event has no predecessor. Then this gotta be 2. Likewise, that's gonna be 3, 4, and 5, right? Okay. And this is exactly same as what he just developed. Okay, now let's compute the earliest time and the latest time based on this AOA network, okay? So this is the one. So as before, we're gonna have latest time and the earliest time for each event. So 0, 1, 2, 3, and 4, and 5 down here. And then let me just disable my camera. Okay. Okay. So starting at time t equals 0, the earliest time for the start node becomes 0. Right? So we have 0. Right there. 0 here, right? So for both activities, A and B, the early start time should be 0. So I'm going to have 0 down here. And earliest finish time for both both activities A and B is going to be 0 plus the duration of that activities. So for A, it's going to be 5. For B, it's going to be 4, right? Because this node number 1, event 1, represents the completion time of the activity B, which is 4, right? So the earliest time for event number 1 is going to be 4. And here we have dummy activity 1, that is no time, okay? And it's going to be the early start time for dummy activities going to be 4 plus 0. So earliest finish time is going to be 4 as well. Okay, now we need to determine the earliest time for event number 2. Because event number 2 is the completion time for both activities A and dummy activity down here. We have to take the larger number between these 5 and 4, right? So we're gonna have 5 here. So for both activities C and D, the earliest start time is gonna be 5. Okay, and then earliest finish time for activity C is gonna be 5 plus 3, which is 8. For D, 5 plus 2 would be 7, right? So earliest time for event number 3 is going to be 7. And earliest start time for activity E is going to be 7. And then earliest finish time for activity E is going to be 7 plus 2, which is 9, right? Again, we need to determine the earliest time for event number 4. That's going to be the larger number between this 8 and 9, right? So that's going to be 9 up here. And earliest start time for activity F going to be 9. 9 plus 3, 12. It's going to be the earliest finish time for activity F. So the earliest start time, the earliest time for event number 5 going to be 12, okay? Okay, now we know that the project can be completed in 12 days or 12 hours, whatever, okay? So we know that the latest time for event number 5 gonna be how much? 12, right? So I'm gonna use different color. So I'm gonna use blue. Okay. So the latest time for event number 5 gonna be 12. And then now we are going to do the backward computation, starting from event number 5 all the way through event number 1, okay? So the latest finish time for activity F gonna be 12, right? 12 minus 3 is gonna be 9. That's the the latest start time for activity F. So the latest time for event number 4 is going to be 9. So the latest finish time for both activities E and C going to be 9. Okay. 9 minus 2, 7. 9 minus 3, 6, right? Because we have latest start time for activity E is 7. So the latest time for event number 3 is going to be 7. Okay. And then we have 7 up here, 7 minus 2, 5, right? Now we need to determine the latest time for event number 2 here. So we're going to take the smallest value this time, right? Between this 6 and 5. It's going to be 5, right? And then again, latest finish time for dummy activity and activity A is going to be 5. Okay, so 5 minus 0 is 5. 5 minus 5 becomes 0, right? And from here, we have 5. And 5 minus 4 becomes 1. Again, it's time to determine the latest time for event number 1. Again, we're going to take the smaller value between 0 and 1, which is 0. Okay, now we've determined the earliest time and the latest time for each event. So now we can determine the critical path, right? So we are going to use the total float. Okay. So for each event, if there is no differences between these two numbers, that's going to be included in the critical path. Or for each activities or task, if there is no differences between these two numbers, the earliest start time and the latest start time, if there is no differences, then that's going to be one of the critical activities. Okay, so I'm going to use green color. Okay. So the critical path should be starting from 0 2, 3, 4, and 5, right? So the critical path is going to be 0, 2, 3, 4, and 5. And the critical activities going to be activity A, right? And then D, right? E and F. And we know that this project can be completed within 12 days. Okay. Okay. Okay, now let's talk about how to set up a linear programming model that can be used to find the critical path. Okay. Although the previous described method for finding a critical path is easily programmed on a computer, the linear programming model can be used to determine the length of the critical path and its critical activities as well. So here, our goal is to find the shortest time required for the completion of the project, right? So in other words, our goal is to minimize the time required to complete the project. So in this AOA network diagram, the event number 0, node number 0 represents the beginning of the project, right? And the event number 5, node number 5, represents the completion of the project. So if we define variable y is the time that the event number I occurs, okay, then our objective function can be represented by minimizing y5, right, minus y0. How's that? Does that make sense? Okay, then what constraints do we need? For every predecessor requirements, we will have an equality constraint. So for example, event number 0 must precede event number 1. Translates to y1 is greater than equal to y0 plus d sub 0, 1. That's because d sub 0, 1, in this case, 4, right? That is the duration for the corresponding activities. So that's going to be y0 plus 4, okay? So this value, y0 plus 4, is the completion time for activity B in this case. Is that right? So this precedence relationship can be nicely represented by this inequality constraint. So we need to do the same thing for the other precedence relationships in this AOA network. Okay, that's what you need to do. Okay, so we just did for arc 0, 1. We have y1 has to be greater than equal to y0 plus the duration, the corresponding activity, which is 4, right? Or let me just write it down. D sub 0, 1. So we have D sub 0, 1, okay? Likewise, for arc 0, 2, we're going to have y2 is greater than equal to y0 plus d sub 0, 2, right? And how about for arc 1, 2? So for arc 1, 2, you're going to have y2 is greater than equal to y1 plus d sub 1, 2, okay? For arc, about 2, 3 then. That's going to be y3 greater than equal to y2 plus d sub 2, 3. About arc 2, 4. y4 greater than equal to y2 plus d sub 2, 4, right? For arc 3, 4, you're going to have y4 greater than equal to y3 plus d sub 3, 4. Finally, for arc 4, 5, you're going to have y5 greater than equal to y4 plus d sub 4, 5. Okay. Okay. And from the, okay, so these are the constraint sets, right? And our objective function is minimizing y5 minus y0, right? And subject to these constraints. Okay. What do we miss? The sign restriction. So actually, we are going to have unrestricted in sign for all I values. This is from 0, 1, 2, up to 5, right? This is because any event can begin at any points in time, in the past, present time, or in the future, right? So that's why we put the unrestricted in sign for every decision variable for this LP model, okay? So the decision variable y sub I can take any positive or negative real values in this case. And one of the variable domain functions in Lingo, I believe it's going to be at free, will be used for this case, okay? Okay, then now let's find the optimal solution and its objective function value using Lingo and Lindo, okay? It's Lingo. Okay. Okay, so let's do that. I'm going to zoom in a little bit. Okay, so let's do that. It's going to be mean. Okay, this is Lingo window, so I'm going to use the Lingo syntax. So mean equals y5 minus y0 in semicolon. And Lingo doesn't need ST or subject to, right? And we just need to type in every constraint just one by one. So y1 is greater than equal to y0 plus what is d01? The duration for activity B is 4. By the way, just to let you know, if you remember, for Lingo, you don't need to move each decision variable to the left-hand side. So I'm going to just leave like this way, okay? But for Lindo, every decision variable has to be located in the left-hand side of each constraint, but not for the Lingo, sorry, okay? So let's do this. Y2 greater than equals y0 plus 5, right? And y2, y1 plus how much is that? 1, 2 is 0, right? So you don't need to put them in here. Okay, let me do this. I'm going to put the comments. So for arc 0, 1, right? For arc 0, 2. For arc 1, 2, right? And then next for arc 2, 3, it's going to be y3 greater than equal to y2 plus 2, right? Okay, that's for arc 2, 3. For arc 2, 4, it's going to be y4 is greater than equal to y2 plus 3. 1, 2, 4. And then 3, 4, right? So y4, y3. Okay, it's fine because it's Lingo both are not case sensitive. So I'm gonna just leave like that. So 3, 4, it's gonna be 2, right? Okay. For arc 3, 4. 1, 3, 4. So there's this typo. And the last one, y5 greater than equal to y4 plus 3. That's for arc 4, 5. And after the ending mark, no, before the ending mark. Okay, I got confused, but should be before the ending mark. We need to include the free variable restriction. So free, and then inside the parentheses, we're gonna list the decision variable one by one. Y0. Let me just copy this and then paste. Then change y1 to y0 to y1 to 3, 4, and 5. Okay. I think that's it. Then let's run it. Okay, now we got the optimal solution right away. Okay. So the objective function value of 12 up here, right? Indicating the project can be completed within 12 days. Okay. So, and then what about the optimal solution? So we need to look at the value of decision variables y0 through y5. Okay. Now I gotta tell you that in general, the value of y variables in any optimal solution can assume any value between the earliest time for each event and the latest time for each event. So it is telling you that the event number 0 can be started like 5 days ago. Event number 1 can be started like yesterday. And event number 5 can be started a week from now on, kind of thing, okay? And this RP actually has many alternative optimal solutions. So this optimal solution just shows one of them, okay? Possible, one of those possibilities. However, all of the optimal solutions of this RP will indicate the length of any critical path is 12 days, okay, up here. But let me ask you a question. Does this optimal solution tells you the critical path? No. Although this RP tells you the length of the critical path, it doesn't provide us which activities are included in the critical path. Is that correct? Okay, now let's go back to our LP model. Okay. And let's think about how to build the dual of this LP model up. So what I did here, okay, so let me get the full screen. So what I did here is to move all of the decision variable to the left-hand side and then sort them out, okay? So we have here same objective function, which is minimizing y5 minus y0, subject to all of these constraints, okay? Of course, we're gonna keep using the unrestricted sign for every decision variables, okay? Okay, so you remember a decision, the dual variable is defined for each primal constraint. And because we have seven primary constraints, right? 1, 2, 3, 4, 5, 6, 7. 7 primary constraints. That's because we have 7 different arcs in this network diagram, right? 1, 2, 3, 4, 5, 6, 7. So because we have 7 primary constraints, we must have 7 decision variables, 7 dual variables, right? Which means there will be a decision, the dual variable for every precedence relationship, precedence restriction of the form. activity I must precede activity J. Okay. And if we define the dual variable, this time we are going to use X sub ij represents the unit flow from event number I to event number J. So we have these set of dual variables, 7 different dual variables, one for each primal constraint. Okay. So using the conversion table, you remember? We've used this table a couple of times, right? This primary LP can be converted to this dual LP, okay? So this is the complete dual LP. Objective function is maximizing this, subject to this constraint, including the decision variable restrictions. And actually, I can tell you that the constraint of the dual LPs are the conservation of flow equations for the AOA project network. So if I assume that one unit of flow originate at event number 0, node number 0, destined for node number 5, then for each node in this project network, we have a flow balance equations. Okay. So the left-hand side of each constraint gonna be the flow into node minus flow out of node. So the difference is gonna be the net flow generated at each node. And the right-hand side value gonna be the net supply value, which is inflow minus outflow at each node. So the value of the right-hand side gonna be negative if the node number I is the supply node, and positive if node number I is the demand node. Unless otherwise, it's gonna be 0. Okay, for all the other nodes, for the transshipment nodes. Okay, so the dual LP is the problem of finding the longest path through the network from node number 0 to node number 5. Okay. Okay, now let's use Lingo or Lindo to find the optimal solution and its objective function value. So again, I'm gonna use Lingo. And okay, so I'm gonna use this. It's gonna be max the okay, duration for activity B is 4, so 4 times x01, right? plus 5 times x02 plus 0 times x12. So I'm not going to include that. Next is 2 times x23 plus 3 times x24 plus 2 times x34 plus 3 times x45. Okay. Oh, sorry. Don't forget semicolon to end the objective function. Now we can type in each constraint one by one. So negative x01 minus x02 is equal to negative 1, negative x12 equals 0, x02 plus x12 minus x23 equals 0, x23 minus x34 equals 0, x24 plus x34 minus x45 equals 0, x45 equals 1. And you don't need to include the non-negativity restriction, right? So I think that's it for Lingo model. Okay, now I got it. I forgot to include equal sign here. So let's try again. Okay, we got the solution. Okay, so here, the optimal objective function value, the same as before, right? 12. So Lingo indicates that this project can be done within 12 days, right? How about looking at the decision variables? The optimal solution tells you this. So from here, Lingo tells you that x01 cannot be included in the critical path. But x02, maybe let me open the Microsoft Word. So that I can write it down. So according to this Lingo optimal solution, to say x01, I'm sorry, x02, x23, x34, x45 has the value of 1, right? Which means these are going to be included in the critical path. So our critical path is going to be 0, 2, 3, 4, and 5. Okay, that's our critical path. And for the critical activity, we need to look at our AOA network diagram. So 0 to 2, right? So we have critical activities. Gonna be A, and then 2, 3, including activity D, and then 3, 4, activity E, and then 4, 5, activity F. So that's gonna be the critical activities, okay? And the project completion time gonna be 12 days. Okay. So that's the things you need to report. Okay. Critical paths, critical activities, and the project completion time. So as you can see here, the dual LP can actually tells you which activities are included in the critical path. But you cannot get that information from the primer LP. Okay. Okay, so before I end today's lecture, let me just do the Lindo modeling to recall your memory. So these are the Lingo model that we developed. So if someone want to do the Lindo model, then what you need to do is go to options, and under the interface tab, you need to check mark LTX and apply. Okay. And then click on the new window. Now just make sure that it does tell you that the Lindo model can be used within this new window. So let me just copy everything from Lingo and then paste it down here. So let's revise this model for fitting in to Lindo. So mean is okay, but you don't need equal sign, and then you don't need semicolon, right? So I'm gonna delete this semicolon for every single line. But you don't need to delete this because the Lindo take everything right after the exclamation mark as comment. So it's up to you. You don't need to delete this. So I'm gonna just leave this. Okay. And okay, one very important thing is for Lindo, every decision variable has to be located in the left-hand side of each constraint. So you need to move this to the left-hand side like this. So I have minus this. To this, okay. negative sign. Okay. It's going to be like that, right? Okay, we don't need positive sign here. We need to put 0 value. Like that, right? Okay, and I think it should be ending mark here. But like Lingo, in Lindo, we need to put the variable restriction right after the ending mark. Okay. And then actually for Lindo, you just need the variable name after the free. So that's going to be just like that. Okay. That's it. Okay, so if you solve it, what is that? Syntax error? Oh, no, I got it. We forgot to put st or subject to right after the objective function. Okay, now it should be okay. See, we got the optimal solution. So it does tells you the project can be completed within 12 days. But again, the optimal solution for this primary LP does not give you the information about which activities are included in the critical path, right? Okay, and one more thing, because every decision variable in this primary LP are restricted to be unrestricted in sign. So instead of listing all of decision variable explicitly like this, you can just count the total number of variables, 1, 2, 3, 4, 5, 6. So I'm going to put 6 and then remove everything. But still, you're going to get the same optimal solution, right? Okay, here. See, this time we have slightly different optimal solution. What is that? Solution for this. Not this one, this one. See, that's from Lingo, and then that's from the Lindo. See, the y variable values are different here. So from this optimal solution, you can interpret like this way. If you start the project like 5 days ago, then the event number 1 has to be started yesterday, and event number 2 will be today, and event number 3 is going to be started 2 days from now on. Number 4 will be started 4 days from now on, and then event number 5 will be started a week later. But for this, you can say that event number 0, the project can be started if the project is started for today, then 4 days later, the event number 1 will be started, and 5 days later, and the event number 2 will be started, and so forth. Okay, because like I said, in general, the optimal solution values, I mean the y variable values in the optimal solution can say that can assume that any values between the early start time for each event and the latest time for each event. So, but it doesn't tell you both cases which activities are included in the critical path. It only tells you that how long it's going to take to complete the entire project, which is 12 days for both cases here. Okay. Oh, today is really dry, so let me drink water. Okay. Okay, so that's for the primary LP, and for the dual LP, it's going to be very simple, right? For Lindo, again, I'm going to copy everything from Lingo and paste it this window, new window. Just make sure every time you type in, before you type in the mathematical model, make sure that you are doing the right thing, depending on the Lindo model or Lingo model. Okay, here. If it does say Lindo model, then you have to put the Lindo syntax, right? So in that case, you're gonna delete equal sign before you type in the objective function. And then we don't need asterisk as the multiplication symbol in Lindo, right? So I'm gonna delete everything here. You don't need semicolon, but before you type in each constraint, don't forget to put ST or subject to. Like that. And then I'm gonna remove semicolon. Okay. And then you got the optimal solution right away. So again, this dual LP tells you the project completion time is going to be 12 days, right? And from the optimal solution, it does tells you the critical path should be 0, 2, 3, 4, 5, right? That's going to be the same as before. What is that? Okay. 0, 2, 3, 4, 5. The corresponding critical activity is going to be ADEF from here, right? Okay. Okay, then I'm going to stop here for today. And next time we will continue to talking about the critical path method. Okay. Thank you. Okay, bye-bye.